Welcome back. In continuation with our earlier discussion regarding Bayes learning, today we are going to discuss the last concept in this unit number 4, and that is Bayesian belief networks. As discussed earlier, the Naive-based classifier makes significant use of the assumption that the values of the attributes, say x1, x2 up to xn, are conditionally independent given the target value y. So we are having here the assumption that the values of the attributes are conditionally independent of one another given the target value y, and this is the most significant assumption that we had under Naive-Bayes classifier. This assumption dramatically reduces the complexity of learning the target function. However, in many cases, this conditional independence assumptions are too restrictive. So, in practice or in reality, having such kind of conditional independence is not possible. And that is why this assumption is too restrictive. But if we are not having such kind of assumption, then the problem may be intractable. So, we would like to come up with some solution that will not be so much restrictive and will consider the conditional dependence in some form. And such learning algorithm or such learning approach is known as Bayesian belief network. Thus, Bayesian belief network is a type of probabilistic graphical model. It is a type of probabilistic graphical model. It is also known as Bayes nets. A Bayesian belief network describes the probability distribution governing a set of variables by specifying a set of conditional independence assumptions along with a set of conditional probabilities. We have seen that in Naive-Bayes classifier, we had an assumption that all the variables are conditionally independent given the value of target variable. But in contrast to the Naive-Bayes classifier, we have Bayesian belief networks that allow to provide or to state conditional independence assumptions that are applied to a subset of the variables, meaning it is allowed under Bayesian belief network to provide the conditional independence assumptions for a particular set of variables. Thus, in essence, Bayesian belief networks provide an intermediate approach that is less constraining than the global assumption of conditional independence made by the Naive-Bayes classifier, but more tractable than avoiding conditional independence assumption altogether. So here we are having some relaxation for this assumption of conditional independence, and that will make this more realistic. Bayesian belief networks are an active research area and a variety of algorithms have been proposed for learning them and for using them for inference. However, we are not going to look at all these algorithms. In this unit, we are going to introduce only the key concepts and the representation of Bayesian belief network. So, what is Bayes network? Typically, it is a kind of probabilistic graphical model. So, let us see now with one simple example how to represent Bayes network. Let us assume that we are having a set of random variables denoted as x1, x2 up to xn, and also we are having a target variable, say y. So, we have a set of variables now in a domain, and we would like to look at the types of dependencies or independencies between these variables, and we are going to make use of Bayesian belief network to represent this scenario. As I mentioned earlier, Bayesian network is a probabilistic graphical model comprising nodes and links or arcs. Nodes are actually representing the random variables, whereas links, edges or arcs are expressing probabilistic relationships between these variables. So now let us try to draw a simple Bayesian belief network having 4 variables x1, x2, x3 and x4. So as I mentioned, these variables x1, x2, x3, x4 will form 4 nodes of the network. So here we can visualize these 4 nodes x1, x2, x3 and x4. Now we are having the arcs in between the nodes. As I mentioned, the arcs represent relations between the variables. If there is no arc, what it means? It means that there is lack of relation between the variables. So let us say that we are having an arc between x1 and x2, x2 and x4 and x3 and x4. What it indicates? It indicates that there is some probabilistic relationship between x1 and x2, between x2 and x4 and between x3 and x4. There is no arc between x1 and x3, hence we may say that there is no relation between x1 and x3. Thus, the arcs are representing conditional dependence relationships between the nodes, and nodes are nothing but the variables. Causality can also be represented using Bayesian network. So what we mean by causality? Causality is efficacy by which one event contributes to the production of another event where the cause is partially responsible for the effect and the effect is partially dependent on the cause. Let me repeat once again, what is causality? It is efficacy by which one event contributes to the production of another event where the cause is partially responsible for the effect and the effect is partially dependent on the cause. So we are having a cause and the effect, those are represented using the graphical notation. Among different variables in the domain, some of these variables may be the causes of the others and some may be the effects of the few variables. if we represent this causality, we get a compact Bayesian network structure. And representation of causality makes the structure of Bayesian network more efficient. So once again, look at the network that we have drawn. We are having x1, x2, x3, x4, those are the variables, and we are having the arcs in between those variables or the nodes. We are having a child node and a parent node. So if the arc is going from x2 to x4, we say that x4 is a node which is a child node and x2 is a node that is a parent node. And there is some conditional dependence between x2 and x4. Also, one important point to be noted is this probabilistic graphical model is a DAG, or it is a directed acyclic graph. Further, associated with every node, we are having some probabilities, and these probabilities are denoted as probability of xi given parent of xi. I will repeat, the probability associated with every node is given as probability of xi given parent of xi. This determines the effect of the parent on that node. I hope you must have understood the concept of Bayesian belief network and how to generate such kind of a graphical model. But to have more clear perception of Bayesian belief network, let us look at one realistic example of Bayesian network. So, Bayesian network is a very important tool in understanding the dependencies among events and assigning probabilities to these events, ascertaining the effect of occurrence of one event given the other. So, let us see one example. Suppose you are late at office or you are late at work. There could be many reasons for being late at work. What might be the reasons? Like you woke up late and this causes you to reach late at work. Further, the reason could be that there is a traffic jam and hence you reached late at work. Here we may say that late at work is an event, and this event is dependent on the events like waking up late or traffic jam. So these reasons have a direct influence on the event that you got late at work. This can be effectively represented using Bayesian network. Let us try to draw it now. So while formulating the problem now, we are having three variables or events like waking up late, traffic jam and late at work. So associated with these three variables, we are having three nodes in our network now. So node for waking up late, node for traffic jam and a node late at work. Here we are having now the dependencies. So what are the dependencies? Due to waking up late, it is possible to get late at work. Also, as there was a traffic jam, this may influence the event late at work. So we are having now two arrows, those are representing these dependencies. So we are having arc from waking up late to late at work, and we are having arc from traffic jam to late at work. So here late at work is a child node and it has two parents, waking up late and traffic jam. Both may influence the node late at work. Thus, the child node's occurrence is influenced by the occurrence of its parent node. Now, let us try to extend this scenario further. So, let us assume we are having one more event, and that is rainy day. So, this event may influence traffic jam. So, let us add this node in our network rainy day, and let us have an arc from rainy day to traffic jam, denoting that rainy day may influence traffic jam. So overall, now we are having 4 events or variables: rainy day, waking up late, traffic jam and late at work. And this network represents how these events are having some kind of relations in between them. So rainy day may influence traffic jam, and traffic jam may influence in turn late at work. Now let us once again refer to our example with few more extensions and try to understand how conditional probabilities and the notions of conditional independence and dependence can be interpreted using this example. So let us have a recap of whatever we have seen in the earlier slide. So suppose you are late at work. There could be many reasons for being late, like waking up late and traffic jams. So here late at work is dependent on the events like waking up late or traffic jam. That is, these reasons have a direct influence on the event that you got late at work. The reason for traffic jam may be due to rain. So there is an event, rainy day, that influences traffic jam. Now let us add 2 more nodes such as accident and late for meeting. Suppose these are the variables which are of our interest, and we would like to see what is the relationship between these variables. Let us say waking up late influences whether you are late for work. If there is an accident, it is more likely that there is a traffic jam. If it is a rainy day, it is likely to be a traffic jam. And maybe we can say if it is a rainy day, there is higher likelihood for an accident. So rainy day can also influence occurrence of an accident. If you are caught in a traffic jam, it affects whether you are late for work. If you are late for work, it affects whether you are late for a meeting. Now the arcs drawn denote the causal relationships between these variables, and from this structure we get a directed acyclic graph that represents the nodes and the relationships between the nodes. And from this network now we can read different conditional independence relationships. Let us try to elaborate more. We can say that late for work is influenced by whether you have woke up late. But you are late at work directly influences whether you are late for meeting, and therefore we can say that if you wake up late, that affects whether you are late for the meeting. I'll repeat it once again. Late at work is influenced by whether you have woke up late or not. But you are late at work directly influences whether you are late for the meeting, and hence we can say that if you woke up late, this event affects whether you are late for the meeting. However, if you know that whether the person is late for work or not, then the interpretation might be different. Suppose you are not late for work in spite of waking up late. Suppose you are not late for work in spite of waking up late. Then whether you are woke up late or not does not influence whether you are late for the meeting if you know whether you are late for work or not. So meaning, if you know that you are not late at work, the value of the event, whether you woke up late or not, will not affect late for meeting, provided you know whether you are late for work or not. So, waking up late and being late for meetings are normally not independent, but they are conditionally independent given that you know whether you are late for work. Please try to understand this concept. So, waking up late and being late for meeting are normally not independent events, but they are conditionally independent given that you know whether you are late for work. Let us see one more case. Look at this event, accident, and another event, waking up late. These two events or these two variables are independent. That is, waking up late is independent of whether an accident has happened. But if you know that you are late for work, then these two variables do not remain independent. Suppose you did not wake up late, then accident could be the reason why you are late for work. So these two variables, waking up late and accident, are not independent if you are given the value of this event, late at work. Thus, this particular graphical representation encodes certain conditional independence relationships. Now, let us define formally and precisely the notion of conditional independence. Let us assume x, y and z are three discrete valued random variables. We say that x is conditionally independent of y given z if the probability distribution governing x is independent of the value of y given the value of z. I'll repeat, x is conditionally independent of y given z if the probability distribution governing x is independent of the value of y given the value of z. That is, if we write it mathematically, we are having the expression as shown here. For all xi, yj, zk, probability of x equal to xi given y equal to yj, z equal to zk is equal to probability of x equal to xi given z equal to zk. That means x is conditionally independent of y given z. We can write the same expression more compactly, like probability of x given yz is equal to probability of x given z. Now let us try to relate our example with this formal definition. Getting late is conditionally independent of rainy day given traffic jam. Getting late is conditionally independent of rainy day given traffic jam. So we are going to write it like this: probability of getting late given rainy day comma traffic jam is equal to probability of getting late given traffic jam. This means that even if getting late is dependent on the two events, rainy day and traffic jam, if we know the value of traffic jam, then we may say that getting late is independent of rainy day given the value of traffic jam. Now let us note the correspondence between this definition and our use of conditional independence in Navy Bayes classifier. The Navy Bayes classifier assumes that the instance attribute x1 is conditionally independent of instance attribute x2 given the target value y, and this allows the Navy Bayes classifier to calculate probability of x1 comma x2 given y as shown here in this expression. By simply using the product rule, we can write probability of x1 comma x2 given y is equal to probability of x1 given x2 comma y into probability of x2 given y. Now, as we know, in Navy Bayes classifier, we are having the assumption that x1 and x2 are conditionally independent. Probability of x1 given x2 comma y becomes probability of x1 given y. So the expression now becomes probability of x1 comma x2 given y is equal to the product of probability of x1 given y and probability of x2 given y. So after going through the formal definition of conditional independence, let us see now what we mean by joint probability distribution. Because Bayesian networks are based upon joint probability distribution and conditional probability. So we know what is conditional probability and conditional independence. So let us try to focus upon joint probability distribution. Assume we have variables capital X1, X2, X3 up to Xn, and let V of xi is in general a variable, so let V of xi denotes the set of possible values of xi. Now to form one tuple, we may pick the values from all those different sets, V of x1, V of x2 up to V of xn. Thus, the probabilities of a different combination of values for the tuple of variables x1, x2 up to xn are known as joint probability distributions. The probability of x1, x2, x3, xn can be written as the expression in terms of the joint probability distribution. So probability of x1, x2, x3 up to xn is equal to probability of x1 given x2, x3 up to xn multiplied by probability of x2, x3 up to xn. Now using chain rule, we can substitute the value of the second term in this expression, that is probability of x2, x3 up to xn. So by expanding this expression, we may write probability of x1, x2, x3 up to xn is equal to probability of x1 given x2, x3 up to xn into probability of x2 given x3, x4 up to xn, so on up to probability of xn minus 1 given xn into probability of xn. In general, we can write the expression as probability of x1, x2 up to xn is equal to product over I equal to 1 to n probability of xi given parents of xi. Here this parents of xi denotes the set of immediate predecessors of node xi in the Bayesian network. Now let us once again get back to our example that we discussed earlier and for which we have drawn the Bayesian network. So let us refer to the figure once again. Let us assume that all these variables in our network are the Boolean variables. And now using the formal theory, we may say that this Bayesian network represents the joint probability distribution over the Boolean variables. In general, a Bayesian network represents the joint probability distribution by specifying a set of conditional independence assumptions represented by a directed acyclic graph together with sets of local conditional probabilities. We know that each variable in the joint space is represented by a node in the Bayesian network. For each variable, two types of information are specified. First, the network arcs represent the assertion that the variable is conditionally independent of its non-descendants in the network given its immediate predecessor in the network. What we mean by a descendant? We say X is a descendant of Y if there is a directed path from Y to X. So I'll narrate the first point once again. The network arcs represent the assertion that the variable is conditionally independent of its non-descendants in the network given its immediate predecessor in the network. And the second information that is specified is regarding CPT. A conditional probability table CPT is given for each variable describing the probability distribution for that variable given the values of its immediate predecessor. So for example, now let us try to look at one condition probability table that is associated with late at work. As I mentioned, CPT for a variable under consideration describes the probability distribution for that variable given the values of its immediate predecessor. So here in our example, let us abbreviate now these three nodes. Late at work is abbreviated as LW. Waking up late is abbreviated as WL, and traffic jam is abbreviated as TJ. So while specifying the conditional probability table for late at work, we are supposed to consider its immediate predecessors, and there are two predecessors for or immediate predecessors for late at work, and these two are waking up late and traffic jam. So CPT for late at work involves the probability values now for these three nodes. Now let us see what we have in this table. The row LW indicates the probability of late at work. Now this probability depends upon its two predecessors, that is two events, waking up late and traffic jam. As all these variables are Boolean, if we consider these two predecessors, we are having four combinations of the values of these two variables. Thus we are having the combinations that WL is true and TJ is also true. WL is true but TJ is false. WL is false and TJ is true, and both WL and TJ are false. So we may interpret now this probability of LW as probability of LW given WL is true and TJ is true is 0.4. Probability of LW given WL is true and TJ is false is 0.1. Probability of LW given WL is false and TJ is true is 0.8, and probability of LW given WL is false and TJ is also false is 0.2. This means that probability of late at work, provided you woke up late and also the traffic jam was there, is 0.4. And similarly, we can interpret other conditional probabilities. Now, once you know the probability that you are late at work, it is possible, or you can easily compute the probability that you are not late at work. So, the probability of not late at work is equal to 1 minus the probability of late at work given the respective conditions. For example, probability of not LW given WL TJ is equal to 1 minus probability of LW given WL TJ. So this is how we have computed all the probabilities for the event not late at work, and all the probabilities are given in the conditional probability table as shown. Now, once the Bayesian network is built, the question remains that how can we infer the probabilities or the values of one or more network variables given the observed values of other variables. If Bayes network contains all the information that is needed, or it contains the values of all the variables, then it is very much easy to infer the probability distribution for the target variable. But if the values for only the subset of variables is known, then in general case the problem is NP hard. The numerous methods have been proposed for probabilistic inference in BayesNet. These methods include exact inference methods and approximate inference methods. The exact inference methods work well for some typical network structures, whereas the approximate inference methods are developed that sacrifice precision to gain the efficiency. Such methods include one of the most popular methods known as Monte Carlo method that simulates the network randomly to compute approximate solutions. Now we have seen how to build the network and what are the different methods to infer the probability values for the target variables from the network. But the most important intermediate step is learning of Bayesian network. There are several variants of this learning task. In some situations, network structure might be known or unknown, and that must be inferred from training data. In certain situations, training examples might provide values of all network variables, or there are only some of the values available. If the structure is known and all the variable values are observed, then it is as easy as training a Navy Bayes classifier. But in many situations, it is not the case. That means the structure might not be known and values of only few of the variables are known. In such situations, the learning task becomes difficult. Now suppose the structure of the network is known and variables are partially observable. So once again, considering our example, let us assume that we can observe the variables like late at work, accident, rainy day, but it is not possible to observe traffic jam, late at meeting, and so on. So such kind of a problem where the variables are partially observable, the learning of Bayesian network becomes similar to training neural network with hidden units. We are not going into the details of any of the learning algorithms for Bayesian network, but this is for information. In fact, one can learn network conditional probability tables or CPTs using the algorithm gradient ascent. Gradient ascent procedure searches through a space of hypotheses that corresponds to the set of all possible entries for conditional probability tables. The objective function that is maximized during gradient ascent is the probability P of D given H of the observed training data D given the hypothesis H. In contrast to gradient descent, in gradient ascent, the convergence of the algorithm is that finding out the hypothesis H that locally maximizes the probability of D given H. Now, let us quickly go through few of the applications of Bayesian networks. Only few of the applications are listed over here: document classification, medicine, especially in the domain of medicine. For diagnosis purpose, the Bayesian networks are being popularly used. For example, you know the symptoms of a disease and you want to identify what is the possible cause. So, from the symptoms, it is possible to find out what is the probability of a specific cause. Or even it can be used for prediction. For example, predicting the symptom given the cause. For example, the cause is the cancer and you are having two symptoms, that is weight loss and having a tumor. So you may find out what is the probability of weight loss or what is the probability that you have a tumor if you have a cancer. That means it can be used for prediction given the cause. So find the probability of the symptom given the cause. That is finding the probability of tumor given cancer. Further, the Bayesian networks can be used for information retrieval, for the tasks such as semantic search, and to solve many problems under the domain of image processing. So having enormous number of applications, the Bayesian network is the popular machine learning approach. So with this, we are going to conclude this unit number 4 regarding probability and Bayes learning. So we covered probability concepts initially. Then we focused upon Bayes theorem. We talked about concept learning. We have seen how to learn a real valued function. Then we discussed Bayes optimal classifier and Gibbs algorithm. We talked about Navy-Bayes classifier and now the Bayesian network. Also, we have solved many of the problems under these concepts. So, I hope you must have understood the concepts and you will definitely try these algorithms for solving real world problems. Thank you.